Hi! Okay, that was my daughter JC. She's the second star of this show. Alright, so this is the second of two videos that you should be watching today. This is about the third type of chi-square procedure, which is called a chi-square test of homogeneity. We're going to be looking at page 10 of our notes, so if you could find page 10. If you have another device to watch this on so you don't have to use your iPad, I would recommend that. That'll save you the trouble from having to do everything on the same device. Okay, page 10. The question asks, do male and female college students have the same distribution of living conditions? Use a level of significance of 0.05. Suppose that 250 randomly selected male college students and 300 randomly selected female college students were asked about their living conditions: dorm, apartment, parents, other. The results are shown in the table below. Okay, so similar to what we had with the chi-square test of independence, we have a two-way table for our data for a chi-square test of homogeneity. Now what you're going to find is that with a test of homogeneity, it's almost exactly the same procedure as a chi-square test of independence. It's essentially the same thing. Okay, there's only some very subtle differences, and one of those differences being the phrasing of your hypotheses and your conclusion. Okay? At the end of this video, I'll also highlight some of those differences because that really is the hardest thing to recognize the difference between homogeneity and independence. Okay, so this particular problem gives us a clue that it is homogeneity, and that is the key word, same or different. Okay, we saw that they asked the question, do male and female college students have the same or different distribution? Because they used that phrase, same or different, rather than the keywords we saw in the previous video, independence, dependence, or association, that's what makes this a test of homogeneity. Homogeneity just means sameness. Okay, so let's check out our hypotheses. Null hypothesis. The null hypothesis here, remember, null means no change or no difference. That's exactly what we're testing. We're assuming that the living conditions of males are the same as, no different from, females. Versus the alternative would be the opposite, that there is a difference. Living conditions of males are different from females. Okay. Once again, notice we wrote out our hypotheses in words. We did not have to define any parameters because we didn't use any symbols in our hypotheses. Let's take a look at our assumptions. Assumptions are exactly the same for the excuse me. Assumptions are exactly the same as our other chi-square procedures. We still have a random sample. In this case, because they took two different samples. In the stem of the problem, you may have recognized that they took a sample of male students and a sample of female students, two different samples. So we are told that both samples, plural, are randomly selected. We also have our 10% condition. We have to assume that both populations are sufficiently large. In this case, n is less than 1/10 the population. We make a statement, there are more than 2,500 male college students and more than 3,000 female college students. Seems reasonable. Our large counts condition, we have to have all of our expected counts to be at least 5. And once again, you're going to use your calculator to do this. I'm not going to show you on the calculator how to do it again. If you watched video 1, hopefully you followed along well enough and you can see how to do this on your calculator. You're basically going to take your observed counts, you're going to put them in a matrix, matrix A in particular, then you're going to run the chi-square test, and then go back and look at matrix B, and matrix B should show you your observed, or should show your expected counts. In this case, all my expected counts are at least 5, 70, 74, 77, 64, 36, etc. And I made a statement that says our sample size is sufficiently large to use chi-square procedures. Remember, when you put your data into matrix, you're going to always put it in as rows by columns. So this would be a 2 by 4 matrix, 2 rows, 4 columns. Okay. Let's turn it over and look at the other side. Uh-oh.
Do you want me to help you?
No, I can hold it. It's about ready to fall over. Okay. So, my chi-square statistic, I just ran this on my calculator, and that's what I would, can you still see this all from when I turned it around? Yeah, okay. The chi-square statistic is 10.13. The calculator gave me the p-value of 0.0175. Degrees of freedom, exactly the same as what we did with a chi-square test of independence. It's rows minus 1 times columns minus 1. So 2 minus 1 times 4 minus 1, and that's where the 3 degrees of freedom comes from. Conclusion, decision, conclusion, all still the same. We're just going to use a slightly different phrasing in our conclusion. We're going to use a phrasing that matches the hypotheses. Okay? Due to a small p-value, we reject the null hypothesis, and we do have statistically significant evidence that male college students have different living conditions than female college students. Okay? That's it. So, if you go on to compare the chi-square test of independence to a chi-square test of association, everything was the same. The only difference was the phrasing in the hypotheses and the phrasing in the conclusion. That's it. Okay? So, down here, I highlighted some of those differences. Okay, and this is probably what I think is the toughest part of independence versus homogeneity, is knowing which to use when. Okay, because you do need to be able to identify which procedure is an independence procedure and which procedure is a homogeneity procedure. So, the first thing is your phrasing. Okay, looking for the keywords, looking for the clue words in the stem of the problem. When we have tests for independence, the keywords that you're looking for are independent, dependent, or association, just like we talked about in the first video. In homogeneity, you're looking for one of these keywords, same as or different from. Okay, when you see those keywords, you can be fairly confident that you have the right procedure. All right. The other difference is how many samples are taken. In a chi-square test of independence, there's always one sample taken. Okay, it's always just one sample only, because there is one sample taken from one population. In a chi-square test of homogeneity, you're always taking 2 or more samples. Okay, so in this case, the one with the college students, we had 2 samples that came from 2 populations: the population of male college students and the population of female college students. The last difference is how many variables there are. With chi-square test of independence, there's always 2 variables. Okay, specifically, we are comparing whether 2 variables are independent in that single population. In a test for homogeneity, it's always one variable. Okay, we're always just comparing one variable with respect to 2 or more populations. Okay? So these are the subtle differences to recognize those. I would write down this chart, make sure you put this in your notes, because you do need to know when you're going to use homogeneity and when you're going to use independence. In practice, the only difference between the two is how you phrase your hypotheses and how you phrase your conclusions. Okay. Thank you.